So now let's talk about epistasis. And with epistasis, it can be confusing. There's a couple different types. There's going to be a lot of different ratios. Make sure it's good to know the ratios off the top of your head, but if you can't just memorize them off the top of your head, make sure you understand how to get them. And even if you do know how to memorize them off the top of your head, make sure you still understand how to get them, because that's the most important part here. So let's talk about what epistasis is to begin with. So something that a lot of people mess up with epistasis is that there are two genes here. This means that you're going to be dealing with a dihybrid. So every single time that we're talking about epistasis, it's a dihybrid. Every single time. I've seen so many students that I tell them it's an epistatic problem, and they start drawing a monohybrid cross and they aren't able to figure it out. That's because this is a dihybrid. Okay, so every single time you have a dihybrid, that's a really important point, and that's the first step in being able to do any of these problems. So since it's a dihybrid, that means that our 9:3 to 3:1 basic ratio might apply. Remember, this is the phenotypic ratio if you are crossing two complete heterozygotes. All right. So with epistasis, basically what's happening is you have one gene that says what color the fur is. And that's what we're used to, where it's like the fur is going to be brown or yellow. Okay, we got that. And then the other gene says, because remember, it's a dihybrid, so your first gene says something, your second gene does another thing. The second one says if there's going to be any color at all. So this gene says, is color going to be made? And if it says yes, color is going to be made, then this one is going to say what color it is. So if this says no color is going to be made, it doesn't matter what color this one was going to be because there's no color made. So we need the gene that says there will be color to work in order for our other gene to matter at all. Let's think of another example. In order to know what color hair someone has, first you need them to actually have hair. So if there's a bald person and you're looking at them, you're not going to know what color their hair is. And it doesn't really matter if their hair is brown or if their hair is blonde because they're bald. It's the same idea here with epistasis. You have one gene that's going to say, do they even have hair? And if they don't have hair, it doesn't matter what color it was going to be. Okay, let's think about this in a non-genetics way. So think about a romantic relationship. Think about the epistatic gene being the boss. So think about a wife and a husband. The husband decides when he wakes up in the morning, he's either going to go mountain biking or backpacking that day. And he goes to his wife and asks her, and she says, absolutely not. You're staying inside and cleaning this whole house. So does it matter that if he was going to go out, that he was going to go backpacking? No, because he's not going out. He's stuck inside. You need the epistatic gene to say, yes, you can go out, in order for the other gene to say, okay, now I'm going to go backpacking. It doesn't matter if the epistatic gene said, nope, you're staying inside. And he was like, well, I was going to go backpacking. He's not going backpacking. He's staying inside. So now let's go through some terminology now that we hopefully have a little bit of a better grasp on what epistasis actually is. So the epistatic gene, like we just mentioned, it's the boss. It determines if the other gene even matters. This is also called the masking gene because it's like the one that determines if there is color at all. So it can mask either the color gene being dominant or recessive. It doesn't matter what it is. It'll not show up no matter what. So this will say if there is color. And then your other gene is going to be called the hypostatic gene. This is the gene that can be masked. So this is the one that says what color it is, brown or blonde. So now there's a couple of types of epistasis. The first one is recessive epistasis. So whenever you're looking at types of epistasis, remember that the word in front is the thing that says, for example, no color. So that's going to be the thing that's masking everything else. So if the recessive genotype says no color, that means that either the heterozygous or homozygous dominant genes would mean there is color. And no color is homozygous recessive. Duplicate recessive epistasis, this one's a little confusing. So In duplicate recessive epistasis, instead of having an epistatic and a hypostatic gene, there's two epistatic genes and no hypostatic gene. So this is the one that's a little bit different than our other two. The last one's going to be dominant. So in this case, with duplicate recessive epistasis, you're going to have two genes, and if either or both are homozygous recessive, there's going to be no color. So if this is little a, no color. If this is big A, and this is little b, no color. If this is little a, and this is little b, no color. So having homozygous recessive in either one of the genes or both of the genes means no color. You need both of these genes to be either homozygous dominant or heterozygous to have color. And our last one, like I said, is dominant epistasis. So remember, the word in front says the thing that's going to be completely hidden. So that means that whenever this gene is dominant, the other gene doesn't matter. It doesn't matter what color it is. So since it's dominant, that means that we only need one of the alleles in order to not have color. So that means that no color would be homozygous dominant or heterozygous. And the only way to actually get color would be little a. All right, so now we're going to go into a couple drawings to try and see if we can derive the ratios and make this little chart make a lot more sense, because I know it was a lot at once. So before we do that, I'm just going to remind you guys of your normal dihybrid ratio. So remember, this is the phenotypic ratio for two heterozygotes. Crossed. Okay. So this is our wonderful 9:3 to 3:1. And we're going to talk about what each of these numbers mean again. It'll be important whenever we go into the epistatic stuff. So this 9 means you have both dominant alleles. So for example, if I was talking about hair color and eye color, where brown is dominant to blonde and brown is dominant to blue, the 9 would be brown hair, brown eyes. 3 is dominant recessive. So same example, brown hair, blue eyes. This other 3 is just the other direction. So that'd be blonde hair, brown eyes. And 1 is recessive, blonde hair, blue eyes. Okay, so now what do the genotypes for these look like? So the genotypes for this dominant one is going to look like this. So remember, since this ratio 9:3 to 3:1 is all about phenotype, that means that whether we're looking at a homozygous dominant or a heterozygous individual right here, they both have the same phenotype. Whether I'm homozygous dominant for brown hair or heterozygous, I'm going to have brown hair because I only need one of those dominant alleles. So dominant, you're always going to have that dash for the second one to account for either possibility, since they both result in the same phenotype. And that's what this ratio is about, phenotypes. So for this dominant recessive, it would look like this. Our first trait is dominant. We only need one, so the other allele doesn't matter there. And then we have our little b for recessive. For this other one, it'd just be the opposite. And our last one, both recessive. Okay. So now I'm going to rewrite this at the very top right here, so we can refer to this as we go. And it is really important that you guys understand where this comes from, and not just knowing the numbers 9:3 to 3:1, but knowing what they mean. That's a pitfall a lot of students fall into, is understanding 9, 3, 3, 1, and just knowing those numbers and then not knowing what they mean at all. Okay, so now what we're going to do is talk about our 3 types of epistasis. So we're going to talk about recessive, duplicate recessive, and dominant. So I'm actually going to do recessive and then dominant and do duplicate recessive last. This is because in recessive and dominant, you have one epistatic gene, one hypostatic gene, and they're normal. And then with duplicate recessive, it's two epistatic. So I'm going to leave that one for last so you can see the comparison between whenever you do have the normal one epistatic, one hypostatic. So first, let's talk about recessive. So in recessive epistasis, and also this is just my personal preference, I always make the second gene the epistatic gene. So I'm going to say that your B is your epistatic gene. And then that would mean that A is my hypostatic gene. So B right now is saying, is there going to be color? And saying yes or no. And then if B says, yes, there's color, then A is going to say what the color is. So in this case, my B allele is going to be the epistatic gene. And because this is recessive epistasis, little b equals no color. So I'm going to continue with this color example. There's other examples. So for example, with recessive epistasis, there's the blood type example where if you're little h, you can't develop antigens at all to become A and B. That's called the Bombay phenotype. Go ahead and look at your notes if that is not familiar to you. But the no color for me is the simplest to understand. So that's the analogy we're going to keep using here. Okay. So little b means no color. So if I go up to my 9 to 3 to 3 to 1, and remember the ratios that we derive for these three types are only going to be relevant if we're crossing two dihybrids, because the ratios that I'm going to make in each of these spots come from the normal crossing two dihybrids. So if you're not crossing two dihybrids, you're going to have to do small monohybrid crosses for each gene and then cross it yourself. Okay, so anytime there's little b, there's no color. So notice there's two spots with little b. And remember, the epistatic gene is just going to mask whatever the other gene is. So for little b right here, it doesn't matter if this is a big A or if it's little a's. It doesn't matter what that other gene is. If this says it's masked, it's masked. So that means that 4 of these would have no color. So that means that anywhere that we have a big B, that means that we do have color. So that would be right here and right here. So 9 are going to have color, obviously, because of that big B. And since they do have color, now that's whenever we can finally look at our A. So if there's no color, it doesn't matter what our A is. But if there is color, then we do have to look at what our A gene is. And in this case, 9 of them are going to have the dominant color, and 3 of them would have the recessive color. Oops, okay. So we have right here a 9 to 4 to 3 ratio. 9 with the dominant color, 4 with no color, 3 with recessive color. Okay, now let's look at the dominant. So again, I'm going to make B my epistatic gene. And in this case, since this is dominant epistasis, that means anytime I have at least one dominant allele, it doesn't matter what that second one is, no color. So let's look at our 9 to 3 to 3 to 1. So that happens right here in the 9 and right here in this 3. So that means that, and again, you'll see it doesn't matter what our A gene is. If our B gene is dominant, it doesn't matter, sorry, if A was dominant or recessive, it's going to get masked either way. So there's a total of 9 plus 3 that are going to have no color at all, which is 12. And then that means in order to have color, in this case, we need to have little b, because anything with a big B means no color. So where do we have little b? Well, we have it right here, and we have it right here. And you notice that with this little b, we have a dominant color, and with this little b, we have the recessive color. So we'll have 3 with dominant color, 1 with recessive color. So in this case, our ratio would be 12 to 3 to 1. 12 with no color, 3 with the dominant color, 1 with the recessive color. So notice in both of these cases that first you always have 3 options: no color, dominant color, recessive color. And your dominant and recessive color can only show up whenever your epistatic gene is allowing the color to exist. So in our recessive epistasis, that means these had to be dominant for your epistatic gene. In our dominant epistasis, that means that these two had to be recessive for their epistatic gene in order for color to even exist. Okay, now let's talk about duplicate recessive, and this one is a little bit weirder because, oops, that's an ugly star. Both A and B are epistatic. And having AA, little a, means no color. Having little b means no color. And it would be any combination of those equals no color. So if you have little a with some big B, no color. Little b with some big A, no color. Little a and little b, no color. So let's go ahead and look at our dihybrid. So first, let's look for anywhere there's a little a. That happens right here and right here. So that means that these 4 automatically no color because of that little a. Now let's look for little b. You'll notice it's also in this one right here, but we already counted that 1 with our little a. So we also have the double recessive right here in this 3. So just looking for anywhere that there's double recessives happens right here, and right here. So that accounts for 3 plus 3 plus 1, which is 7. So that means that 7 of them are going to be able to have no color. And again, it doesn't matter if one of them is recessive, the other one is dominant. As long as one of them is recessive, no color. So that means that 7 have no color. And our last option is going to be this 9 over here, since that has both of them dominant. And that 9 would just have color. So notice the difference between duplicate recessive and the other ones. In the other ones, we have a recessive color, a dominant color, and no color. So there's 3 options. So like you have no color, and then you have color, and in color, there's 2 options for a total of 3. In duplicate recessive, because it's both epistatic genes, there's just color or no color, and that's your only options there. So I highly recommend that you guys take some time with this. I know it's confusing. Try and draw out what I just did on your own time. Take a break from the video for like an hour or 2 and see if you can go and draw these ratios and if you understand where they're coming from. Just make sure you spend some time with it, do some practice problems with it. It will make sense the more that you practice, but I do know it's really confusing when you first hear it. All right, so that's the end of our epistatic video, and our next one will be over sex influence traits.
I hope you found this video really helpful. The concepts and information presented in these videos will be true no matter what genetics class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are currently enrolled as a Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need to know about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online through Navigate, or just drop in during our open business hours. For more information about our current services, please visit our website. Thank you.